We just found the electric potential due to a point charge. Think back to how we dealt with electric fields. As soon as we knew the electric field from a point charge, then we said, what happens if we have multiple point charges? Let's take a look at that situation with electric potential. Let's look at this situation. We have 2 point charges located as shown, a positive Q and a negative 3Q. We want to know what's the electric potential at the origin if it's 0 at infinity. The potential at the origin is going to be a combination, the sum of the potential from charge 1 and the potential from charge 2. Let's add them up and see what we get. Am I forgetting anything? Up until now, we've been pounding into you, electric field is a vector quantity. Don't forget to break it up into components before you add things together. But electric potential is a scalar. You will be happy to know. So we don't have to worry about components. We just have to add them up. But we do have to be careful with signs. For Q1, I have to put in a positive value because it's positive charge. And for Q2, I have to put in a negative value. The electric potential could end up being positive, negative, or even 0 if the numbers cancel out. Let's see what we get in this case. In this case, the potential at the origin is negative. Let's think about what that means for a second. At the origin, our potential is negative. It's 0 at infinity. The electric field always points toward lower potential. The electric field basically points from infinity to the origin. Of course, it's going to have a convoluted shape, but basically it points toward the origin. It has to have some net component toward the origin because the potential is lower there than at infinity. Remember, potential is a scalar, and with scalars, a negative number is less than 0. Negative 5 is a smaller number than negative 3, is smaller than 0. So already I know some things about the field in this area. It basically points from infinity to 0. So if I have a charge, a positive charge at infinity, and I let go of it, the field will push it toward the origin. The field will do positive work on my charge and move it toward the origin. Because of that, I know that the potential energy has to change. The potential energy of the field particle system has to change. If I put a particle at infinity and let go of it, it's going to gain kinetic energy as it's pushed toward the origin by this field, and therefore the potential energy in the system is going to go down. So you want to kind of think through things like that. What direction does the electric field point? If I move a positive charge in that direction, is it going to gain energy or lose energy? That means that the potential energy in the system has to change. But you can reason through those pretty quickly. Next thing we did with electric fields, we said if we can treat every little element of a continuous charge distribution like a point charge and add up all their contributions to the total electric field, we can find the electric field due to a charge distribution. That's what we're going to do with the electric potential. Let's find the electric potential above the midpoint of a charged rod. We'll follow the same thought process we did for electric field from a charge distribution. We pick some arbitrary little chunk of charge, dq, and say that is contributing to the total potential at that location, and its contribution is dV. And how do we find the potential due to this little chunk of charge? We treat it like a point charge, and we say the potential is K times the charge over the distance. The distance is from dq to our point of interest, the hypotenuse of this triangle. That's x, the other side is a, and the hypotenuse is r. Now, I want to add up all the contributions. And because this is a scalar quantity, we don't have to worry about components. So we can just add up all the contributions. What is dq? Same thing we got with electric fields. It's lambda, the charge density, multiplied by our length element. And in this case, because we're along the x-axis and it's a straight line, it's dx. And once we know what we want to integrate with respect to, we want to turn everything into that variable. So everything in terms of x's. So let's change our r into x's, and we can do that by looking at our right triangle. And we get x squared plus a squared square root for r. And we are integrating over the entire charge distribution from minus L over 2 to plus L over 2. Now I look this up on an integral table, and I got k times lambda. Those are my constants. And the natural log of x plus the square root of x squared plus a squared, evaluated from minus L over 2 to plus L over 2. Because this is symmetric, I can say this is 2 times the integral evaluated from 0 to plus L over 2. Makes it a little easier to evaluate. And this is the potential at distance a above the midpoint of a charged rod of length L.